meter, it works on the same principle as that of the Venturimeter works. So it is a very simple device. It is a simple circular plate having opening at the center, and this orifice opening diameter is generally half the pipe diameter. So here you will find the mounting of orifice plate in a pipe, where you can see the flow is getting converged when the flow enters the orifice plate, and it gets further converged, and you will find the diameter of the jet coming out from the orifice plate is minimum at point 2, and this point 2 section is known as vena contracta region, where you will find the jet diameter less than the orifice opening diameter. So if you observe the diagram carefully, you will find that there is a wake region around the vena contracta, and this wake region is responsible for the losses in the measurement. So it is same as that of the Venturimeter. So you will find the two legs of the U-tube differential manometers are attached at point 1 and point 2. So at point 1 the pressure, velocity and datum head is P1, V1 and Z1, while at the point 2 the pressure, velocity and datum head is P2, V2 and Z2. So the pressure at point 1 would be more than that of the pressure at point 2. So we will get a manometric head difference as delta H, and we can establish a relationship between piezometric head difference and the manometric head difference very easily. The piezometric head at point 1 can be written as P1 upon rho g plus Z1, and the piezometric head at point 2 may be written as P2 upon rho g plus Z2, and the difference between the piezometric head at point 1 and point 2 is nothing but small h, and this small h is equal to P1 upon rho g plus Z1 minus P2 upon rho g plus Z2. So that means it is the piezometric head difference between the piezometric head available at point 1 and point 2. Let rho m and rho w are the densities of manometric and working fluid. So the relationship between H and delta H is small h is equal to rho m upon rho w minus 1 into delta H. So applying the Bernoulli's theorem between the point 1 and point 2, assuming the ideal fluid flow, it is P1 upon rho g plus V1 square upon 2g plus Z1 is equal to P2 upon rho g plus V2 square upon 2g plus Z2. Rearranging the equation 3, we will get P1 upon rho g plus Z1 minus P2 upon rho g plus Z2 is equal to V2 square upon 2g minus V1 square upon 2g. So this rearrangement we have done to obtain the piezometric head difference. So ultimately small h is equal to V2 square upon 2g minus V1 square upon 2g. Applying the continuity equation, as the flow is incompressible, so rho 1 is equal to rho 2 is equal to rho, and q theoretical is equal to a1 v1 is equal to a2 v2, and based on this the velocity at point 1 v1 is equal to a2 upon a1 into v2. Putting the v1 in the equation 4, so you will get p1 upon rho g plus z1 minus p2 upon rho g plus z2 is equal to v2 square upon 2g minus 1 upon 2g. Now putting the value of v1 in this at the v1's place, that is a2 upon a1 v2 bracket square. So simplifying the equation, you will get h is equal to v2 square upon 2g in bracket 1 minus a2 square minus, not minus, 1 minus a2. I'll repeat this. H is equal to v2 square upon 2g in bracket 1 minus a2 square upon a1 square. So equating the denominators of the term in bracket, so you will get h is equal to v2 square upon 2g in bracket a1 square minus a2 square upon a1 square. Now to obtain the value of V2, we will arrange the various terms. So by rearranging, you will get V2 is equal to a1 root of 2gh upon root of a1 square minus a2 square. Now putting the value of V2 from the equation 8 into the equation number 5, so we will get a q theoretical is equal to a2 into V2, and putting the value of V2 you will get q theoretical is equal to a1 a2 root of 2gh upon root of a1 square minus a2 square. But in actual, the losses always occurs in a real fluid flow, hence the actual discharge is always less than the theoretical discharge. Hence we have a term called as coefficient of discharge. So the coefficient of discharge is the ratio of actual discharge to the theoretical discharge. CD is equal to q actual upon q theoretical. So based on this, q actual is equal to cd into q theoretical. So putting the value of q theoretical from the equation number 9, you will get q actual is equal to cd into a1 a2 root of 2gs divided by root of a1 square minus a2 square. Now for the Venturimeter, the coefficient of discharge is 0.95 to 0.99, while for the Orifice meter it is 0.6 to 0.65. So here you will find the difference between the coefficient of discharge for the Orifice meter and Venturimeter. If you compare this, you will find the discharge coefficient of discharge of the Orifice meter is less than the Venturimeter. So it has a reason that in case of Venturimeter, if you observe the construction carefully, you will find a throat section where the second leg of the differential U-tube manometer is attached. And in case of Orifice meter, where the second lead is attached, it is attached at the vena contracta, and vena contracta is surrounded by wake region. So because of this, there always occurs a EDs, and this EDs will lead to the variation in delta H reading, and this gives a inaccurate delta H reading, and because of this, the coefficient of discharge for the Orifice meter is always less as compared with the Venturimeter, as Venturimeter is having throat section which is having uniform diameter. So the it acts as a pressure stabilizer over there, and because of this there is very less deflection in a delta H reading, while in case of Orifice meter it is a large deflection. So accurate delta H measurement in Venturimeter and inaccurate delta H measurement in Orifice, that leads to the variation in coefficient of discharge. So this is all for the this lecture on Orifice meter. We will come with the numericals on the Orifice meter and Venturimeter in the next lecture. Thank you.